Okay, so welcome back. So this time we want to talk about whether or not this infinite series, sum of k goes from 1 to infinity, of the square root of k over k cubed plus 1. I want to talk about whether or not this series converges. So what we're looking for is a series to compare it with, right? So kind of like the last example, we kind of got a little approximation of what it looked like this series was roughly approximately equal to. All right, and that's what we compared it to. All right, so we compared it by taking the one sequence of terms divided by the formula for the other sequence of terms, the one we're choosing. So that's what we're kind of looking for, is something to compare it to. So the idea to do that is, okay, as k is getting really big, square root of k over k cubed plus 1, that would be the same as looking at square root of k over k cubed. The plus 1 is really not going to contribute much. And that could simplify down to 1 over k squared. But the square root of 1 over k squared is 1 over k. So it seems like this thing is closely related to the series 1 over k. Now we know that the infinite series 1 over k diverges because that's a harmonic series. So our suspicion now is that this series is going to also diverge, since it seems to be very closely related to it. But we don't know that yet until we compute, use the limit comparison test, which is going to compare this sequence to this sequence, or this series to this series, to that series. And remember, we're basically looking for two things. If the limit of the two things approaches a number, then since my harmonic series diverges, then my series will also diverge. Or the other one we'd be looking at is when we do this fraction, does it approach infinity? Because since the harmonic diverges, then we'll know ours will also diverge. So this is the two things we're looking for. If we run into something like this, then we're going to have to try some other comparison. So we begin to look at this here, limit as k goes to infinity of top sequence there, a over k cubed plus 1. And we're comparing that to the 1 over k sequence. Now, before I start trying to invoke something like L'Hopital's rule here, because let's be honest, the derivative of that top is not something I really want to think about computing. So I'm going to do some algebraic simplifying first. Since I'm dividing by 1 over k, right, that would be the same as multiplying the top by k. But since the top involves a square root, I'd like that k that I have here to be able to enter the square root. So when I would multiply by k, I'd say, well, as k is going to infinity, that's the same as the square root of k squared. Square root of k squared, remember, is absolute value of k, but as we're going to positive infinity, absolute value of k would just be k. So I'm multiplying by k, but I'm transforming a little bit the way it looks, so I can get that k squared into the square root. And so I can do that, and it just multiplies right in. And our problem would now look like this. Square root of k cubed over k cubed plus 1. And we can say to ourselves, hey, as we're going to infinity, that's really just going to be k cubed over k cubed, right? Because the plus 1 isn't going to matter. And that'll just be square root of 1. And so the overall limit is 1. So now that tells me that my two series either both converge or both diverge, because the limit approaches the number. And so since the harmonic series diverges, then we know that our series, the sum of the square root of k over k cubed plus 1, we know it diverges as well. It diverges as well.